Hi, welcome to 4 Honors. I'm Kirk Weiler. Today, we're going to be looking at Unit 4, Lesson number 3 on continuous growth in the number e. I want to give a special shout out to my students who might be on an honors chemistry field trip today. I hope that this lesson helps you out a little bit and helps you enjoy the chemistry field trip some more. So let's take a look at the bulk or at the startup exercise in this lesson. All right. In exercise number 1, we're just going to work with some percents like we've been working with for the last few lessons. It tells us that we have a bacteria that's growing at a pretty robust rate of 6.5% per day, and it has an initial population given by p sub 0. So we don't really know what it is, which probably implies it doesn't matter very much in the problem. Anyway, let's take a look at letter A. Letter A asks us to write an equation for the population of the bacteria, capital P sub t, as a function of the number of days since the population was p sub 0. All right, you should know how to do this at this point, so pause the video for a moment and write down your equation. All right, we're all set. So as we know, right, when we write an exponential equation, we've got our p of t, and what we know is that we always take what we start with, in this case p sub 0, and we multiply it by something. In this case, we multiply it by 1.065. Right? Each day that goes by, we get to multiply by that again. So the number of times we multiply it by is the number of days, t. All right, that's simple enough. Let's take a look at letter B. Letter B asks, what is the percent growth of the population per week? So by what percent is it going to be larger at the end of a week? And what is the percent growth rate per hour? That might be a little bit trickier to think about. But this is a direct extension of a lesson that we did on repeatedly applying percents. So pause the video again now and see if you can figure out what its percent growth rate is per week and per hour. All right, pause the video now. All right, let's take a look at it. If we want to think about it on a weekly basis, then the real question is, again, if we were going to multiply just once, what would we multiply by? Well, we know we're getting to multiply by 1.065 per day, so after a week we get to multiply by that 7 times. If we work this out on our graphing calculator, or any really calculator, it's 1.55398, and so that leads us to understand that our weekly growth rate is 55.4%. On the other hand, per hour is a little bit trickier. Remember, here we're going backwards, right? If we're repeatedly applying it, then to go backwards, we're going to actually use a root, right? So we would do 1.065, and after an hour, we would have only gotten to raise it to 1/24th of a day. Think about how consistent that is, right? So this is the hourly process that's going on. This one, of course, becomes a much smaller decimal. It's 1.0026, etc. You have to be a little bit careful. It would be very simple, very, very easy to assume that it's 2.6%, but in fact, it's 0.3%. All right, so just a little bit of a warm-up. Now, where this is leading us is to a somewhat confusing topic known as continuous growth and modeling in terms of the number e. So anytime we do things continuously, and we'll see this in the next lesson when we look at compound interest, but whenever we do something continuously, we often get the number e involved. For reasons that you'll understand a little bit better in calculus, we can take any model that is written with the standard y equals a times b to the t, and we can write it instead as y equals a times e to the kt. Now, in this model, you should be very comfortable with what the two letters stand for. A is the initial amount, and B is the multiplier that we're getting per 1 unit of time, whatever that is, year, hour, month, day, etc. On the other hand, A times e to the kt, right? E is just that number 2.71. A is still the initial amount, but now we have this extra constant. Remember, t is a variable, so is y. But this extra constant k is what's known sometimes as the growth rate. We're going to call it the continuous growth rate. What I'm going to do is I'm going to go to another slide for a second. We're going to scrub this out. Go to another slide because I really want to compare this, I call it a yearly form, although that's not a great term because T can be in things other than years, versus what's known as the continuous form. I really want to take a look at these two. So they really are fairly similar. The A's are definitely the same, and so are the T's, right? So comparing sort of apples to apples, what we really see is that B and e to the k are the same number. Now you might kind of say to yourself, wait a second, that seems a little bit weird that you can just sort of randomly put parentheses in there. But remember, we have this exponent law that says if I've got something raised to a power, like e raised to the k, and then I raise it to the t, well, then I can multiply those two powers together. In fact, throughout continuous compounding, what I really want you to understand is that e to the k is what we're getting to multiply by for every 1 unit of time, year, hour, day, etc. All right, let's scrub that out and go on to the next slide. This is a very easy formula to apply, but the key is that you should only be applying it if you know that the growth rate that you've been given is what's known as a continuous growth rate. So take a look at exercise number 2. It tells us that we have an area of an oil spill that's increasing at a continuous growth rate of 3.6% per hour. There's a good time unit. Always make sure you know your time units. Per hour, since it first reached a size of 30 square meters. So in other words, that's our initial size. Letter A asks us to write an equation that models the area of the spill with our continuous form, a e to the kt. If you think you know how to sort of substitute everything into this formula and have kind of a nice finished formula, pause the video now. If not, I'll do it in just a second. All right. Let's take a look. It's really pretty easy. The area of the spill, well, A is our initial amount of anything, in which case that's 30, times e to the 0.036. We do not use 1.036. We literally use that rate in terms of a decimal. And again, what this is really saying is that we're multiplying by e to the 0.036 for every, I guess in this case, hour that goes by. Now, what's interesting is letter B. It asks us by what actual percent does the oil spill increase in an hour? Because ironically, even though we're being told that we have a continuous growth rate of 3.6% per hour, the thing's not actually growing at 3.6% per hour. That's really strange. But it's easy to figure out how much it is growing per hour, right? Because all we need to do is understand what we're multiplying by each hour. And what we're multiplying by each hour is just that e to the k, right? So if we just figure out what e to the 0.036 is on our calculator, and that's pretty easy, it's 1.03665, then what we know is that we're growing at actually 3.7% per hour, right? Because this is the number we would have to multiply by after an hour, and that gives us 3.7%. The second question asks us by what percent are we growing every 5 hours? If you think you can figure this one out, pause the video right now. All right, well, there's two ways to do this. You can either say, well, let me write down my 5-hour time interval. You can either say, well, I'm doing this and just multiplying by 5, or you can think of it as this number, which is the same as this number, raised to the 5th. Either way, what we'll get, let me see what our answer is. Can't do this in my head. Anybody who thinks they can, boy, I'd love to talk to you. You must be an interesting person. But this is going to give us 19.7% growth per hour. Seriously, anything involving E, nearly impossible to do with any accuracy in here. So, 19.7% growth per 5 hours, 3.7% growth per hour. And again, what's really interesting is a comparison between the 3.6% growth that they tell us that we're getting, but continuous, versus what we actually get. All right, let's take a look at the next problem. This is sort of a bigger problem, and it gets into radioactive decay. So some of you are actually studying this right now in your chemistry classes. All right. So in this problem, we're told that we have a radioactive material that can be modeled, the amount that's radioactive, by one of these a times e to the kt problems. Okay, where a sub 0 represents the initial amount of material that's radioactive. And the first question that we're asked is, what is the continuous growth rate as a percent? Now this is a little bit weird, so I'd like you to think about it, maybe pause the video, and the answer you write down might look a little bit strange. All right, and let's take a look why. Strangely enough, get rid of that very weird dot. Strangely enough, our continuous growth rate is negative 4.2%. This number, in decimal form that is, always gives us the continuous percent growth. Whether it's a negative growth, in which case it's actually declining, or a positive growth depends on the context of the problem. All right, in letter B, we're asked to investigate on our calculator in order to determine the half-life. Now, what's really interesting about half-life problems and general exponential growth and decay problems is that they don't depend on the initial amount. In fact, all we really want to know is how many hours it's going to take for this multiplier to reach a value of 0.5. So what I do is I take this and I throw it into my calculator as if I'm going to graph it, but instead I look at a table of values. And this is what I see. If I scan through the table of values, and typically I use X here, and then this is Y, I end up seeing something like this. At 16 years, I find that I'm close to a 0.5 multiplier, but not quite, 0.51069. At 17 years, I'm at 0.48968. So my half-life amount of time must be somewhere around that. I would then go in and do what's called refining my table. So in other words, I would go by smaller amounts. And what I would find if I went into the 16s is that at 16.5, we are really close. We're at 0.50007, and at 16.6, we're at 0.49798, and therefore my half-life is 16.5 years. Now letter C asks, by what percent of the original substance remains after 2 half-lives have passed? Verify by examining this on the table. If you think you know the answer to this, pause the video for a second and figure it out. My daughter Evie is wandering around a little bit in the background, so we'll see if she comes in and pays us a visit. But see if you can figure this out. Pause the video now. All right, let's take a look. Did you say 25%? I hope. Because really, it doesn't matter how long the half-life is. The idea is if we get to multiply by half once, and then we get to multiply by half twice, of course we end up with 0.25, so 25%. Now the way that you would verify this on your calculator is you'd go up and you would take a look again at e to the negative 0.042t and evaluate it at 2 half-lives. So what do we know? We know 1 half-life is 16.5, so 2 half-lives would be 33 years. And that does give you a number that's very close to 0.5. She didn't come and visit. Oh well, camera shy perhaps. I'm a little bit surprised. Whoa, I don't know how that just happened. Let's, too late. Let's scrub it all. Going on to the next page. All right, number 4 is one of my favorites. It's one of these comparison problems. We want to figure out what would have the larger, greater annual percent growth, a population that grows at 0.58% per month, or a population that we're told that grows at a continuous rate of 7% per year. See if you can figure out right now which of these has the larger growth rate on a yearly basis. Pause the video now. All right, let's go through it. We just really want to lay it out, right? We want to take a look. Of course, we have to have a pen in order to do it. Let's take a look first at this one that gives us information about our monthly growth rate, right? So we know that every month we would be getting to multiply by this amount. And you got to really watch out. It would be very easy to go with 1 point, right? So it's 1.0058. Watch those zeros. And we want to raise this expression, either way, to the 12th to figure out what I get to multiply after an entire year. So that ends up being 1.07186, I believe. Let me check my answers. Yep. And so that tells us that on a monthly, if with this monthly growth of 0.58%, we're growing at about 7.19% per year. Now, what's weird is that the continuous one almost seems like it's only growing at 7% per year, but that's not. In the next lesson, we'll call that a nominal rate, in name only. What it's really growing at is e to the 0.07, right? That's what we get to multiply by every 1 year. So we work that out, and our answers are 1.07258 for a whopping 7.25% growth rate per year. And so the continuous wins, slightly higher, 7.25 versus 7.19. Ooh, I just got a text message or an email. I don't know, I can never figure out which noise is which. How about you? Let's take a look at the last problem. In the last problem, exercise number 5, it says that Mr. Weiler needs a sustained caffeine level in his blood of at least 45 milligrams or he gets very irate. This is a very realistic problem. It says caffeine is metabolized, used up by the body at a continuous rate of 17% per hour. Graphically, we want to determine the number of hours to the nearest tenth that it will take before Mr. Weiler, i.e. me, gets irate. All right, if you think you can get all the way through this problem, pause the video now and see what you can do. If not, we'll pause it a couple times as we go through it. All right, let's start taking a look at how we do it. Let's model the amount of caffeine that I have in my bloodstream. The amount is going to be that initial amount, 150, times e raised to the negative 0.17 t, right? Because I'm losing it at 17% per hour, negative 0.17. And what I want to do is I want to figure out when that's going to hit 45. Now, eventually, we're going to be solving these types of equations with logarithms. Previously, when we were looking at half-life in exercise 3, we did it with tables. But right now, what I would do is I would take my calculator out and I would put this in one equation, maybe call it y1, put this in another equation, call it y2, and I'd create some kind of a graph. And what's going to happen is the graph is going to look something like this. It's going to be a decreasing exponential and a horizontal line, right? And that intersection point is the time that you're going to want. Now, if you haven't found that yet, pause the video now and try to find that intersection point. All right, so what do we want? We want the number of hours it's going to take before I get irate. If you did this correctly to the nearest tenth, you would find 7.1 hours. I'll show you a graph of it in just a second, okay? But hopefully you found 7.1 hours. Let's scrub the ink. And there it is, right? So we've got this nice decreasing exponential, which intersects that line. So this is our A equals 150 e to the negative 0.17 t. I know that the equation's up here, but it's a little bit hard to see it. This is our horizontal line, y equals 45, and they intersect roughly at 7.1 hours. I think it's 7.08 to the nearest hundredth, but we can take that quite a bit farther. All right, well, that's our lesson on continuous growth in the number e. We're going to follow this up in the next lesson by looking at compound interest and continuously compounding. But for now, I'm going to say goodbye. Thank you for joining me. I'm Kirk Weiler. Until next time, keep thinking and keep solving problems.